Okay, good morning, everyone. Welcome to today's first session, and we are very happy to have Dr. Wasserman from Oxford, who will tell us about Cohen-Macaulay, simplicial computations, and dualising.
Absolutely. Thanks for doing that. Really happy to be here. It's been a really great time in this beautiful place so far, and looking forward to the rest of the week. So I want to talk to you about a project I've been running with Ric Wade, who's a geometric group theorist, and kind of the overall theme of the project is to bring some tools from algebraic topology to be more accessible to geometric group theorists. And the thing that this is all about is something like a Poincar&eacute duality for the cohomology of discrete infinite groups, and kind of comparing that to the same kind of duality for infinite but still locally finite simplicial complexes. So the long-term goal of this project, which we haven't achieved just yet, is to characterize duality groups topologically, or geometrically. We'll see that there are some things that you might need to have in terms of geometry. So the kind of naive ideal statement that you would dream of getting is that if G is a duality group, that would happen if and only if it admits a classifying space with duality. This turns out to be false, and we have a counterexample that I can tell you about if you ask me questions at all. So my outline for today is that I'll first give you a brief overview of duality groups, and then I'll introduce the kind of simplicial complexes, Cohen-Macaulay simplicial complexes that have the kind of duality that we think relate to the duality groups. And then I'll spend a bit of time discussing what we can do in the interplay of the two and some applications. All right. So, duality groups. I realize this is it's going to be an introduction for about half of the audience is really boring. About half of the audience might be necessary. So bear with me. I hope I'll present it in a way that's at least entertaining. So I'm talking about discrete groups, and I'll pick some module of this group. And then many of you will know that the cohomology of the group is defined in the following way. So the cohomology of G, the coefficients in the module M, is defined just purely algebraically as the case X group of Z and over the ring. So this is just something that's purely algebraic. There's a topological counterpart to this, just a cohomology of the classifying space with coefficients in curly n. Okay, that's not very good curly n. That's a better curly n. And where curly n is a locally constant sheaf on BG that can build by realizing that locally constant sheaves are the same interpretation fundamentally. So you can pass between the algebraic description And the topological description, by doing this representation here. So this is topological. Now, similarly, we have that the homology of G with coefficients in M is defined to be a Tor group, so the derived functor of tensor product, or for the group ring of Z and M. And again, you have this relationship between the homology of the classifying space and the homology of the groups and the coefficients in this module, and the homology of the classifying space, where now instead of taking a sheaf, we take a co-sheaf. So if you're familiar with the notion of a sheaf, it's a contravariant functor out of the partially ordered set of opens of a topological space. The co-sheaf is the dual for this. It's just a functor out of the set of opens, closed opens into Beating groups. And similarly to how you form this locally constant sheaf, you can form a locally constant co-sheaf that corresponds to this representation.
I have a question. When you're defining the homogeneous vector co-sheaf, what does the derived functors of? I mean, for a sheaf, it's global sections.
Yeah. So in the setup I have, I can. In the setup we have, we do it directly by writing down a particular chain complex. This is not the derived functor of the section functor. It's the derived functor of some co-section. But that particular construction only works in the setup that we have. Otherwise, you have to essentially, read red on and off. Thanks. Okay. Any other questions?
Yeah. BG is a topological space, and we can define homology for every module. So if you ignore these representative, if you go for the locally constant equal to constant sheet, do you have a map between these two homologies?
Sorry, I don't think I understood your question.
What?
I don't think I understood your question.
I was wondering, I mean, you can define HK of PGM, you just plug in the model of turning it into a constant sheet like this.
Yeah,
model.
I mean, you could, but that's just the cohomology of PG with coefficients in the obedient.
Exactly. So I was wondering what the relation between these two is. Containing that information.
Yeah, I mean, so I think maybe another way of saying it is that M is a local coefficient system.
Mm-hmm.
So you're asking me what's the relationship between a local coefficient system with an interesting representation of the fundamental group and the local coefficient system with the same underlying median group, but no interesting action.
Yes.
And I don't have a good answer. Okay, I think they're inherently very complex.
There's no universal coefficients or anything like that. It's completely undefined.
Yeah. Okay. Anything else? Okay. So with all of these definitions in hand, I can tell you what a duality is. And to kind of ease you into it, I'll first tell you what a Poincar duality is. And so vector G is called an orientable n-dimensional Poincar duality group if for all in M and choices of coefficient modules, we have that the cohomology of the group with coefficients in the module is related to the homology with coefficients in that module in degree n minus a. And just to be clear, so this map is actually given by a cat product with a fundamental class. So what are examples of these orientable n-dimensional punctuated relative groups? Well, for example, if you take the fundamental groups of or take fundamental groups of surfaces, orientable surfaces, they will give you examples of punctuated relative groups. Now, for those of you who have done an algebraic topology course, this probably doesn't come as a surprise. I can get rid of this orientable at the cost of tensoring here with a sign representation. So you can talk about punctuated relative groups, where you just allow your group to act at least by a sign on the local coefficient system. And then more generally, a large class of these punctuated relative groups is just fundamental groups of asymmetrical little manifolds. So, well, that backs the question. So I give you a very large class of examples. In fact, we don't know any finitely presented punctuated relative groups that are not pi1 of a closed state spherical. So this is something that goes back to Wall, was the first, I think, to study punctuated relative groups. So he asked this question, and somewhere in the 90s, Davis came along and gave examples of non-finitely presented groups, punctuated relative groups that are not the fundamental group of the manifold. And the finitely presented case is just open. Okay, so that's punctuated relative groups. The thing I want to talk about is a little bit more general. So there are called duality groups. So I'm going to modify my definition of punctuated relative group to make it into the definition of duality group. So G is called an n-dimensional duality group if so the new thing is that there now exists a module D, which I'll refer to as the dualising module. Such that for all K and all M, you have this isomorphism where now instead of getting an isomorphism between just the homology coefficients in M, you get homology with coefficients in M tensored with this module, where I should point out that this tensor product is the tensor product over Z with action. So it's not the tensor product of the ring. So it's the tensor product over Z with that. And so the way you think of this is that, in passing from orientable punctuated relative group to a punctuated relative group, we started allowing for tensor in the sign representation. Now we just take it a step further. We just take some representation G that we allow ourselves to transform. So a bunch of examples. So like many of these examples are up to passing into a finite limit subgroup or virtual, as it's often called. So, well, the first class of examples, which is the main motivation for the work that Ric and I have been doing, is this series of groups. So free groups are examples of duality groups, but also their automorphisms and their automorphisms. And then there's a nice paper by Brady and Meyer that shows that many right-angled arcing groups are duality groups, and you can even read off. So a right-angled arcing group is something that you define using a graph. You can read off from the graph whether your group is going to be duality. With some computational work. Then something I know less about, but which is important to mention, is that many arithmetic groups are also duality groups.
Well, we did a dualizing model and all this.
Thanks. Good question, Rudy. I will say a few words about that later. Thanks.
I thought all arithmetic groups were duality groups.
Okay, sure. I said that this is something I don't know much about, but thanks for the addition. Apparently all are. Good. Yeah. Okay, so to give you a little bit of a feel for what's going on with these duality groups, let me kind of state what I think deserves to be called the fundamental theorem of duality groups. So this is from the same paper by Beery and Ekman from '73 that introduced these duality groups. And so what the theorem says is that a group G of type FP. So I don't think that everybody here will know what type FP means. So type FP means that the ground ring has a resolution over the group ring of finite length by finitely generated projective modules. So this is a kind of an algebraic finiteness condition in the group. If you have such a group, and it is a duality, then it is a duality group of dimension. And if and only if this holds, so if and only if the homology of the group with coefficients in the group ring is Z ordered to be in exactly the dimension you want, and zero elements. And
I think that in a duality group always had type FP, so it's like it's stated less strongly than it could be.
oh, yes. And it turns out that and it turns out that n is always the v is just like muscle memory.
It wasn't false.
Yeah, but it's muscle memory at this point. Yeah, so it turns out that n is always the homological dimension of G. So the highest dimension in homology can occur. Okay, now maybe some of you have been reading quick and have already worked out what the bit in gray between the characterization of D and this cohomology group ring is. But we have at least an abstract description of the dualizing module. So if G is n-dimensional duality group, then well, we can do a little computation. We can use the duality to go from the n cohomology group to the zero homology group G. With coefficients in the group ring tensor with D, and by the characterization of Tor of the homology as being Tor, this is just the value of the tensor product of ZG. The group ring tensors with D over the group ring, which is just the module itself. So you just get D. So this gives you an abstract characterization, but to get to answering Rudy's question. So in general, this D is hard to compute directly. There are some really nice proofs, like for example, it turns out that matter class groups of surfaces are duality groups. And there's a really cool proof that shows that the dualizing module is the same as the homology of the curve complex. But like those are things that are like those require like pretty hefty proofs. And just computing this directly is that's not something we do. Okay. So yeah, before I move on to talking about the homological side, any more questions about the duality proofs? Right. Notice that giving a tablet tool is quicker than a board tool, so I'll try and slow down a bit. Okay. Okay, so first of all, I'm gonna like just recall you what Poincar duality says, but I'm gonna do this in a way that may not be familiar to everybody in the room. So, and the thing I need for this is the local homology of the space. So, for a space X and a point in X, this group here, the relative homology X relative to X minus a point, is called the local homology of X at X. And I'll denote it by this little h lower star X. The reason for this is that you can assemble this into a sheaf whose solves are exactly these groups. You, strictly speaking, need to do some sheafification here still, but yeah, I'm going to ignore that sheaf.
So is the sheaf you just take homology of the sections over U, you have a pre-sheaf that's just U goes to homology of X relative to X minus C, and then you sheafify that? That's what you're saying?
Exactly. Or the other ways saying is that you build a Hal space whose solves are exactly the thing I wrote down, and then you take sections.
Okay.
So similarly,
So that Hal space would be like the orientation cover on the output, for instance, right? You have the two orientations.
I mean, the two things in the orientation cover as kind of the sort of the sphere,
Right, yeah.
side of it. Yeah, that's the units. And so similarly, we have the local homology of sheaf by just taking the local cohomology of the space. Now, what does Poincar duality say? Well, it says that if M is an N manifold, then there exists a fundamental class which, if M is not compact, lives in locally finite overall Moore homology of M with coefficients in this local cohomology co-sheaf, which is such that capping with this fundamental class provides an isomorphism from the cohomology of M with coefficients in the local homology sheaf to just the homology of M with coefficient Z. So that's stated in a bit of a weird way. So let me clarify how this relates to the way you know love talking about Poincar duality. So if you're a manifold, then it turns out by the Euclidean property that the bulk at every point is just a property of Z. And if M is orientable, and if M is orientable, then the local homology sheaf just trivializes to the trivial sheaf set, and you're happy to cover the usual statements. If M is not orientable without boundary, you have the following thing. So you have that this local homology sheaf is Z shifted to degree N for points in the interior of the manifold, and 0 for points in the manifold. And so this way of taking the Poincar duality theorem also incorporates Lefschetz duality by realizing if your sheaf enters in the boundary, it's like taking relative homology.
Well, there's a point here I just realized. So you're taking the direct sum of all in all degrees. You're incorporating the dimension. Like this definition gives something even whatever. Okay.
Yeah.
This is like a graded sheet or something, right?
Yeah, this is a sheaf with graded reading groups.
Right.
The reason I'm allowing myself to be a little bit careless with this is that in both this manifold case and in the Cohen-Macaulay case, the sheaf will just be concentrated in a single degree, so you can kind of budget it. Yeah, any more questions about this slightly weird statement of duality? Okay, so the reason I stated it this way is that this kind of leads to a nice way of generalizing this. So I'll generalize Poincar duality using the following definition. So I'll say that the space X is called locally Cohen-Macaulay if for all X in X, the local homology groups are concentrated in a single degree, torsion free there, and 0 otherwise. There's maybe a little warning to give here. Is that Quillen also has a notion of Cohen-Macaulay, but that is phrased in terms of the links of points, and so that's kind of multiple information, not homology information. So if you have seen the word homology in definitely more like the algebraic topology world, it's often used to mean this homotopable condition. The one I mean here is this homological condition. It's just a little warning. Homotopable condition implies.
Is this what's usually called like a post-set homologically Cohen-Macaulay?
Yeah, I mean you can call it homology.
Yeah. But I'm saying like I think that's a common notion, right?
Yeah, but it is used in this way in combinatorial topology.
Yeah.
So there's a bit of a field divide in how people talk about this. Okay. Cool. So what are examples of this? Well, one kind of the easiest example, or the kind of easiest interesting example is simplicial trees. So these are particular EGs for free groups. Another interesting example is color-open outer space. So for those of you who were here last week, this is the thing that Karen told me about. Space with graphs. And so this is a classifying space of proper actions for Allen. Okay, what else? Well, turns out that solventi complexes or their universal covers are both also Cohen-Macaulay spaces. So whenever you have a rack, whenever you want these rack Artin groups that has duality, then you can show that like the natural classifying space associated to the rack has this Cohen-Macaulay property as well.
Do you have a characterization of racks with duality?
Yes. So there's a paper by Brady and Meyer. I think this is the right spelling of Meyer.
'93.
Thanks. That's earlier than this, but more like 30 passes. But thanks for getting me out of it.
Is this thing that the bulk outer space, is that this paper built in like the local structure of outer space? Is that's the one you think of? Yeah.
Yeah, and so as you are probably aware, there are many different like tweaks and versions of outer space. And one of the idea is to establish that a simplicial version of dual space also has this only property, but that relies heavily on that paper. Okay. Well, and generally, maybe just to point out, so what this kind of looks like is that you have what CM kind of looks like is that you have a space in which, or a simplicial complex, in which simplices are allowed to form codimension one singularities, like the one I just formed. Okay, so well, maybe so you might notice that all the examples I pulled up here are examples of either classifying spaces or EGs for duality groups. And the thing that that you can notice is that seemingly all finitely presented B is not really necessary apparently. Virtual duality groups have made locally CM a locally Cohen-Macaulay interactable space with free co-compact action. So that's another way of saying G, EG, and if you want to look at virtual duality groups, you need to add in the word proper, but that's just okay. So so this is the main motivation for the work we've been doing is that in nature it seems that duality groups come with these CM simplicial complexes. So so what we then proceeded to do is prove that these CM complexes can be path-like. So so here's a quick version of the theorem. I'll put it out in a second. So this has a bit of a long history. So there's work of Zeeman and McCrory from like way back in the 60s and 70s that also studied generalizations from duality. And they got very close to writing down a result like this. Another way of looking at this result is that there's this very general duality for sheaves on manifolds called Berger duality. And so Berger duality tells you that there's always a kind of duality statement if you allow yourself to work with derived sheaves or sheaves of chain complexes, where the dualizing module is replaced by a complex sheaves. And from Berger, there's a way of proving Poincar duality from Berger duality, which just uses the chain complex, like the chain complex for manifold ends up being consolidated in sequence 3. You can kind of modify this proof to get a version of this Cohen-Macaulay duality.
Is this related? There's like an exercise in Ken Brown's book that shows that every group is a duality group with a dualizing complex rather than.
Yeah, it's very much. Yeah, though. I wish it was related in as easy a way as possible. It's a little bit okay. So what's the duality result we have? Well, the duality result we have says that if X is an n-dimensional locally Cohen-Macaulay and locally finite simplicial complex, then there exists a fundamental class, which, just like we stated in the Poincar duality, lives in the locally finite homology of the local cohomology sheet, which is such that if you calculate this class, you get an isomorphism between the cohomology of the local homology with compact support and the homology of the space with coefficients in Z. Now it turns out that you can tweak this a bit. You can also prove that you can instead start in the Z homology and then end up in the local cohomology homology. The other thing you can do, which you can also do for Poincar duality, is you can get rid of the compact support if you're willing to work with locally finite homology. So those are just basic things you can do. The thing I decided not to write down for this talk, but the other thing you can do is that you can also prove relative versions of this, so relative to subcomplexes, and you can even take coefficients in arbitrary co-sheaves. You then need to tweak a bit what you mean by the local cohomology. You need to take local cohomology with coefficients in the co-sheaf. But if you're interested there. Okay. Any questions about this? What we also prove is that this is natural.
It's a one-dimensional simplicial complex. CM doesn't have the CM property from the problem. We mentioned the tree case.
Yeah, those and stuff.
Okay, what's the fundamental class then?
I think I was planning on writing that down. Bear with me. I need to tell you a bit more about the set. It's an easy thing to say, but it's easy to say in general. So one thing that we also show is that this is natural. You need to be a bit careful about what class of maps you allow. You can't just allow any map. Maps need to be essentially local homomorphisms, but then this map, this duality isomorphism is natural. And so in particular, if you have a group acting by homomorphisms on a space, on a simplicial complex, then this thing is a covariant. Isomorphisms are covariant. So the thing that we were very keen on doing is to make this very explicit. So we have explicit simplicial formulas using the following tools. So we use something that is often called combinatorial sheaves in the literature. So what are those? Well, you can take a simplicial complex and you can view it as a closed-set for a category by just taking the partial ordered set of simplices ordered to conclusion. And you can look at functors from this into immediate groups. So a simplicial combinatorial sheaf is just a functor from the closed set of simplices into repeating groups. And then similarly, combinatorial closed sheaves are just functors on the opposite of this closed set. And to give you an example,
Is there no like sheaf or co-sheaf condition? There are no vectors.
no, so the trick here is that you only specify the value of the sheaf on essentially local stars of simplices. And so you just don't get any interesting co-cycle conditions because you essentially you want to know the value of the sheaf on an arbitrary open. First of all, it needs to be a union of stars, and then you just impose the sheaf condition.
Nice. Okay.
Yeah, that's because I guess the sheaf condition is not very good. You want to get around it. Okay, so the example. So I'll give you an example of a co-sheaf. So
something these are sort of like a souped up version of just giving the stocks, and then you say, well, you sheaf the
yeah. So something you can prove, which we just did for entertainment, is that these combinatorial sheaves are exactly the same as what are called constructible sheaves, subordinate to the stratification of your simplicial complex by the opposite stratification of the simplicial structure.
Nice. So they're like locally constant.
Yeah, they're locally constant. Or in the interior systems. Okay, so as an example, so you can build a local cohomology co-sheaf by just taking the cohomology of X relative to the open star of whatever simplex you want to evaluate. And of course, that's only the data of what you assign. And then for the co-restrictions, you take whenever sigma is contained in tau, I need to produce the map from the value at tau to the value at sigma. And the way I do this is I just use the inclusion of pairs, which takes X relative to the open star. So you just have this inclusion of pairs, and you run through like I think it's 3 times that this recursions arrow direction. You find out that it's mapped right. So that's an example. I should probably do it here. Answer your question. Okay, so if X is n-dimensional, then H upper star of alpha is just generated by, or H upper star, I'm sorry, H upper n of alpha is just generated by alpha for alpha and n simplex. Right, so you can show that it's not that hard to convince yourself that if you look at the maximal simplex, the only thing you see in the local homology of the maximal simplex is the maximal simplex. And so, what I can do is I can write my fundamental class as the class of the sum over all n simplices of the generator associated to the n simplex in the local homology. So that answers your question. So you take for each maximal simplex, you take the class and local homology of that simplex, which is given by just the simplex itself, or dual.
Don't you need some sort of orientation? Like to make it like isn't there like a choice you're making for each simplex to an orientation or something?
Yes, that's so. Just the reason I'm a bit slow to answer some more works true at this level. So for the duality statement, you need to fix an orientation for sufficient context in the sense that you need to fix an orientation of these syntax. And this construction, well, takes an orientation into account, but does not depend on the end. So that's why I was yeah, that's maybe a detail if you want to know more about it. Okay. Cool. So I think I have some time to just give you a very brief scratch. So so the proof is essentially just analyzing an explicit spectral sequence. So what we do, so first of all, we set up like the cat product for these combinatorial sheaves and their cohomologies, and things like this. And then the core of the proof of duality statement is to explicitly analyze something that looks like well, it looks like a hypercohomology spectral sequence. I am happy to. This is more of a teaser for if you want to know more after. So the way you set this up is you just take a double complex that you build by putting in degree KL, the sum over all L simplices of the chain complex that computes the local homology at that simplex. Okay. And it turns out that this double complex that the homology of this double complex is just a homology space with coefficients set. So the spectral sequence collapses when X is Cohen-Macaulay of dimension n to give an isomorphism between well, it turns out to be the rows on the eacute page and the homology double complex, which is the homology space. So that's like the reason it collapses is just that this chain complex, the homology of the chain complex gets concentrated in a single degree, and then it's left with a class focus. And what is abstractly not that important, but explicitly very important, is that this map goes from the homology into the cohomology. It's along this edge homomorphism. And we construct, so part of what makes this a bit hard is that we want to have an explicit map that you can compare to the cat product. So we can construct an explicit inverse to this map, and go to the degrees with the cat product. So that's very briefly the idea. And yeah, like I said, this is all done in this language, combinatorial sheaves and co-sheaves. Easy to compute. Okay. So a bit about applications and further directions. So one kind of question or intuition that people have is that one question is that is whether the boundary of color outer space is somehow related to the dualizing module for out of n. And the reason this is expected is that this is what happens with mapping class groups, essentially. And what we show in our paper is that dualizing module of out of n, or the appropriate finite index subgroup of out of n, satisfies the following. So the dualizing module, whenever you have an EG, the dualizing module with n-dimensional duality group is always going to be the degree n compactly supported cohomology of that EG, the coefficients in Z. And so what our duality statement allows us to realize that this is the same as the zero homology of the spine of outer space with coefficients in its slope cohomology sheet. So here I have to note by xn the so-called spine. So this is a co-compact Cohen-Macaulay E underbar G or out of n. While on the other hand, the boundary, so this is a bit of a lie that I'm happy to talk about after the talk. So the boundary of outer space has the following property. So it's related. So its homology is related to the dualizing module in this way. So there's kind of a mismatch between what you would want for the cohomology of the boundary and the dualizing module for them to be agreed. So, and as Andy mentioned, there's no universal coefficient theorem for these kinds of sheaves. So the relation between the dualizing module out of n and this boundary of the outer space is subtle, and it's something that, well, we still have some ideas about how to push it a bit further, but this is kind of the first roadblock to meet. Now, just kind of grand further questions. So you can ask yourself kind of the analogous questions to the Wald-Davis questions. So you can ask, first of all, if G acts freely and co-compactly on a contractible CN space X, you can ask to formulate conditions on the group and simplicial complex that will give you from knowing those that G is a duality group. So we know that there is this goes back to work of Gegen. So there's a way of looking at semi-stability for sections of the local homology sheet and getting some results like this, and we want to find something that is stronger than that. And then kind of the Wald-Davis type question. So if G is a finitely presented duality group, does G then admit a co-compact Cohen-Macaulay EG? And so that question is probably quite hard, but it's probably a bit easier than the manifold question because it's just simply easier to be a CM complex than it is to be a manifold. Right. A little bit under time, but I think I'll stop.
Very much.
So I have two questions. So one is, you have this, I'm sorry, I hope I didn't jump around, but I can see. But
Perks of the
this, so you have this H0 of Xn with coefficients in this co-sheet. Is there a sort of concrete interpretation of what H0 means in this context?
Yeah, so this thing here, you can describe this as certain kinds of homomorphisms out of the global sections of the local homology sheet. But I need to put a little declaration here. So these are homomorphisms that have the property that they only see the value of the section of the vertical.
I see.
So that's a characterization. And so this holds, should be honest, so this holds under semi-stability assumption. But those semi-stability assumptions are satisfied.
And my other question is, I guess in this further question, so I guess the sort of obvious condition on X, which doesn't use anything about Cohen-Macaulay-ness, would be that it's compactly supported cohomology, it's concentrated in a single degree of degree, right? So it's like how is that related to like so that's pretty classical. How's that related to CM stuff?
Well, you can try and prove that by trying to evaluate with the zeroth homology of the space with coefficients that homology is. Yeah, so that's something we've been thinking about. The other thing that I should point out is that if you are a duality group and you're acting on the CM complex, then you're classifying places also cohomology. So you're in a situation where you have like after the group duality, so the purely algebraic one. And on the other hand, you have this Cohen-Macaulay duality, which comes from the topology of the classifying space. And one thing that we don't really know how to do yet is how to relate those two. But you have two duality statements. That one involves non-locally constant sheaves, the other one is just for locally constant sheaves. And they're definitely related, but we don't really know how. So that's another.
So what's easy non-example of the group? What is an easy non-example of the group? Example which doesn't satisfy it.
Oh, which is not duality. One example is just this, like take two tori and mention.
Could you explain the reason why?
Yeah, I mean, just compute the homology of the wedge of two tori. And you'll see that there's a homology in degree 2.
I mean, if it's like Z mod 2, anything with torsion will not be.
Yes, yeah. I designed it wrong. But that's maybe also very good to point out is that any finite group will have an infinite classifying space, infinite dimensional classifying space, and so it has no chance of having this kind of duality.
So do you remember the characterization for radius? This is an example of the radius, right?
Yeah, I know. So you need. Okay, let's just say not on top of my head. Like it feels close.
But it classical contour duality, if I have a closed mountain, so I have the intersection pairing and I see a cycle inside a manifold. So contour duality tells me that there is another cycle which in general position intersect my first cycle algebraically once. Is there something like that in your simplicial complex approach?
Yeah, I mean, I don't know this, but my guess would be that you can get an interpretation like that where, at the intersection, the local homology can keep track of kind of which direction you intersected in. So you might need to replace the algebraic count by a count of the
Cohomology. Yeah. With your
yeah, but that's not something I really thought about. It's just a guess I'm making that. So
thank you.
The dualizing model that you have, I mean, you said it's 3Z1, right?
No, it's not. I don't know of an example of a group where it isn't.
Okay.
But for if the dualizing module is free as a Z module, then you also have the duality where you twist the cohomology group rather than the homology. So you have something like H upper star G with coefficients in my variance is going to be all over the place. I think it's something like this. I'm guessing a little bit, so don't hold me to this one. So, but anyways, let me just show you like the twist of homology rather than the cohomology. So that duality is there if and only if the dualizing module happens to be Z3. And so what we do ask for is for it to be Z torsion free, which is
I'm fairly certain it's an open question whether.
Yeah.
There is such. Okay.
My questions. If not, that's when we speak again.